Okay, I really wanted to make sure that you had enough example problems, but I didn't want them to be too easy. I didn't want them too hard, so I'm doing both, the easy and the hard. So let's start with number 23, which should be a little more interesting than the last video. And it just wants us to evaluate this integral. Sine of natural log of 2x. No, I don't want to do this one. This is identical almost to what we did in the lecture video. So we're gonna, let's do 25. Natural log squared of x, okay? You can write it with the squared like this or the squared somewhere else. It's up to you. They mean the same thing. You have two options here. If you wanted to, you could maybe rewrite this as natural log of x times natural log of x dx and think about a integration by parts here. You could try some sort of u substitution. You could try some sort of integration by parts. Lots of options here. I don't actually know the best option. Here's my gut. My gut says that we either do integration by parts, with this being our u, or we do a u substitution. And a u substitution might not work, but let's try it and see what happens. If we do a u substitution, we get du is 1 over x dx, or dx is x times du. So if u is ln x, this becomes u squared times dx, which is almost good, but we don't have an x. But we can get one. If u is ln x, what's x? X is e to the u. Right? This is the logarithmic form. This is the exponential form. They're equivalent forms. Or you can think about exponentiating both sides to get the same equation as well. Because e to the natural log of x, they're inverse functions. They cancel out. Either way, what we're going to get is u squared e to the u du. And I'm not going to finish this problem because we've basically already done it. Integration by parts twice. And then put everything back in terms of x at the end. So you'll have, and then remember that e to the ln x is just equal to x. You'll need to use this. So those are the three things to, again, the answer is in the back of the book. But this is how to start, and those are the three things that you're going to be aware of to get to the answer. $35, same idea, x inverse secant of x. Maybe we use u substitution, maybe we use integration by parts, maybe we use something else. It doesn't tell us. We need a u, we need a dv if we're using integration by parts. Integration by parts looks pretty good because there's two things. Normally this is easy to differentiate, and normally this is what we want. However, we don't want to integrate this. We'll let this be our u, and this be our dv, and go from there. If u is inverse secant of x, du is, it's something like this with an absolute value. Maybe like x squared. This is my guess. Hold on. We should double check this. Derivative of inverse secant. 1 over absolute value x, square root of x squared minus 1. Whoa, nice. Great. Okay. So we guessed right. So dv is x dx. So v is just 1/2 x squared. So this doesn't look great. Let's do the first step in integration by parts, see how it looks. Maybe we'll backtrack. Maybe we'll keep going. I think it'll probably work, but maybe it doesn't. We get uv to 1/2 x squared times inverse secant x minus the integral of v du. 1/2 x squared times, this has a dx here, 1 over absolute x squared minus 1 dx, like so. Let's look at that second integral. Let's clean it up and see if there's something we can do with it or whether we need to backtrack. We get x squared on the top divided by absolute x square root of x squared minus 1. So this doesn't look great. But I'm sure there's something that we can do with this. Interesting. So if x is positive, we get some sort of cancellation. So right off the bat, we can simplify this a little bit. X squared over the absolute value of x is just the absolute value of x. So that's true. So now the weird thing comes into play here is we're finding a general formula for an antiderivative. And so we don't know whether we're looking at positive x or negative x. If x is positive, then it's easy. If we know whether x is positive or negative, this is easy. If we don't know, it's not easy. And I think the book might not make that distinction, is what I'm worried about. So I'm curious. Well, it actually let me open this up. I'm curious what the book ends up doing here. Does it just assume that x is positive? Because that is really important. So we're looking at number 35 here. Yeah, they just assume that x is positive is what it looks like. I don't think we can make that assumption though. Let's play with it and see what happens. Let's say that this is an antiderivative for positive x. Maybe it doesn't matter. Maybe that's why. I feel like it should matter. But maybe it doesn't. Let's assume x is positive and see where we go from there. Let's let w be x squared minus 1. So dw is 2x dx. And if we're assuming that x is positive, we're going to get rid of this absolute value up here, which I don't like, but let's play with that. This first thing stays the same, 1/2. And then we are doing a w substitution. So we just need a 2 here. We have to compensate by putting a 2 down here. Oh, so this is now going to be 1/4. And now this is just dw. And we're left with 1 over the square root of u. Sorry, 1 over the square root of w. dw, and we can just use the power rule. All right, so when we do that, again, this first thing just stays the same. I dropped an x somehow. Use the power rule, we add an exponent and divide by that exponent. Plus c, 1/2 x squared, inverse secant of x minus 1/2. The square root of w. What is the square root of w? The square root of x squared minus 1. And I guess in this antiderivative, right? This formula here, it doesn't matter whether x is positive or negative. And maybe that's why they get away with it. I'd have to maybe think about it a little bit more. But I'm pretty sure this is exactly what they have as the answer as well. Oh, they factor out a 1/2 x from everything. But if you distribute that, you get negative 1/2 x square root of 1 minus 1 over x squared. Oh, wait, that's not the same. Oh, yes, it is. Because, So I spent a moment thinking about, do we really need that assumption that x is positive? Because if x is positive, this is the answer. And if x is negative, right, if x is negative, the only thing that changes is that the absolute value of x becomes a negative x. So the only thing that changes is that the second thing looks like this. And so the question is there just a nicer way to write this? And that's where the book's answer really comes from on this problem, is if we factor out an x, then we can sort of take care of it in two birds with one stone, like this piece over here. Because we can write this guy as 1/2 times the square root of x squared times the square root of 1 minus 1 over x squared. So as long as x is not equal to 0, if x is equal to 0, we have all sorts of problems. And this is really something that comes up in antiderivatives all the time, is whenever we have things that aren't continuous or things that have weird domains, then it gets a little tricky. And so this right here is just x. It's absolute value of x, really. But if we want to really just kind of make it work, then what we can do is just put this as straight up x to combine both of our answers. Because if we write it like this way, if x is positive, then we do indeed get this. And if x is negative, then we do indeed get this. Because this is just the positive version of that. So that's where the book's answer comes from. And then they factor out a negative 1/2, or a negative 1/2 x, or a positive 1/2 x. I think they factor out a negative 1/2 x on this sort of thing. No, it's a positive 1/2 x, but then they leave the negative right there. Got it. Okay, so that is one way that you can combine both answers. Make an assumption for positive, and then see what happens when it's negative, and then we can just combine both of them using what we know about absolute values. All right, so that's kind of an interesting problem. Glad I chose it. That was 35. Let's do two more. 247. Evaluate the cosine of x times the natural log of sine of x. I have no idea what this is going to look like, but it looked tricky. So I thought it'd be fun to do, fun for us to talk about. So we need something to differentiate, something to integrate. If we're using integration by parts, I think I don't want to integrate this. Let's differentiate it. Let's be our dv. So u is going to be the natural log of sine of x. Du will be 1 over sine of x. Chain rule, cosine of x. Dx, that's cotangent. dv is cosine of x. Whoa, let's be consistent. dv is cosine of x dx. Its antiderivative is sine of x. Integration by parts says that we get u times v, which is sine of x times the natural log of sine of x, minus the integral of v du, which is sine x divided by sine x. Oh. This sucks. Times, oh no, it doesn't. Times cosine of x. I thought we almost had something really bad happen. Right, v du is actually really nice. Just cosine dx. Right, because that cancels out. So you get sine of x. Oh, this is not bad at all. I thought we were going to have one of those like cyclical integrals where you have to do it twice and then add something over to the second side. Minus just the integral of cosine of x dx. Antiderivative of cosine is sine. Yeah, not too bad at all. And we can check our answer by taking the derivative. Take the derivative, we get derivative of the first times the original second, plus the first, whoa, times the derivative of the second, and then we get a minus cosine of x from before. And again, this is plus cosine of x minus cosine of x, and this is our integrand, checks out. Great. Oh, that was way better than I thought it was going to be. 63. Find the area under the graph of secant cubed from 0 to 1. What does secant cubed look like? That's not something... I'm pretty sure it's just going to look kind of like this from 0 to 1. I think this will be our area. Let's see if I'm right. Clear all this stuff we don't need. Great. Oh. All right, there's no asymptote. I was a little worried that there was an asymptote. I didn't think there should have been, but... All right, from 0 to 1. So we have the point 1, comma, secant of 1 cubed. Secant of 1 cubed is 1 over cosine of 1 cubed. Oh, wait, we don't know what that is. We don't know what cosine of 1 is. Why is it mad at this? Oh, because I accidentally put a subscript. Okay, so we're looking for the area under this curve. Right. Yep. The area under this curve is just going to be that integral. It'll be the integral from x goes from 0 to 1 of secant cubed of x dx. Now, we don't know how to take this antiderivative. We do know how to take its derivative. We could try integration by parts right off the bat. Or we could try to make things a little bit cleaner. One of the things that I want to look at, I don't know if it'll work, is what if we look at this as secant squared times secant of x? Because we know the derivative of tangent is secant squared. So we know how to integrate secant squared. We know the derivative of secant is not too bad. So this is one way to start this. And I think this is probably the most promising way. You could try a couple other things as well. Let's see where this goes. I don't know if this will work. Du will be the derivative of secant, which is secant times tangent. dv is secant squared. V is tangent. So we're just hoping that this doesn't get worse. So u times v, which is secant times tangent, minus the integral, again, this is from 0 to 1, of v du. Tangent x times secant x tangent x. Is this good? I don't think it's necessarily worse. That's tangent squared. Is there a u substitution? Is there integration by parts on this second one? We could write things in terms of sine and cosines. That gives us sine squared divided by cosine cubed. There are some things that we can do with that. Sine squared over cosine cubed. I don't know if that's what they want us to do, but it's something that we can do with it. Look at this. So the first one is, again, secant of 1, tangent of 1, minus secant of 0, tangent of 0, minus the integral from 0 to 1. Let's write this tangent as sine over cosine, and secant as 1 over cosine. I'm sure this is not the only way to do this. So a u substitution is not really going to help us. Integration by parts is not really going to help us. And so what I'm going to do is either going to work or be a mistake. So let's play with it. So let's write sine squared as 1 minus cosine squared. What does that lead us to? Again, maybe this will work. Maybe this won't work. 1 over cosine cubed is secant cubed. And then we're subtracting a negative. So the second one just becomes secant. This is what we started with. But we can add it to both sides. So this will work. There might be an easier way of doing this. I'm not sure. But I do know that this will work. So we get secant of 1 times tangent of 1, whatever the heck that is. And then minus this integral that we're going to be looking at soon. I forgot my dx. And then plus the antiderivative of secant. Antiderivative of secant is one of those really weird ones. There's a couple of ways of doing it. One of the ways is with integration by parts. We've done it before. You can use integration by parts. I don't want to do it again. So I'm just going to skip that part because we've done it before. It's natural log of absolute secant plus tangent. Again, you can use integration by parts on this guy. Evaluated from 0 to 1. I won't write the bar again. Okay, so what does that tell us? Right? That tells us that the integral from 0 to 1 of secant cubed dx is equal to this whole thing. We can just add this integral to both sides. You get that 2 times the integral from 0 to 1 of secant cubed of x dx is secant of 1 tangent of 1 plus, well, this becomes the natural log of secant of 1 plus tangent of 1 minus the natural log. Secant of 0 is 1. It's 1 over cosine of 0. Tangent of 0 is 0. 1 plus 0 is 1. Natural log of 1 is 0. Great, that all goes away. Divide both sides by 2. And that is going to give us 1/2 secant of 1 tangent of 1 plus the natural log of the absolute value of secant of 1 plus tangent of 1. That's as simplified as it gets. Let's check this with a calculator and see if I'm right. All right, so get a decimal approximation. 1/2 secant of 1 times tangent of 1 plus the natural log of secant of 1 plus tangent of 1. Is that the integral from 0 to 1 of secant of x cubed? Whoa! Not that I'm surprised, of course. Not that I'm surprised. It's the right answer. It's about 2.054. And we're asking about area. So units squared. There it is. Fun little problem to finish off this video. Let me know if you have any questions, and bye-bye.